Alright, so we're going to do problem 4.11 part B. And so if you remember in part A, well, not if you remember, I usually have to go back to the last video. DC we said was K2 over S squared. We said it had to be, K2 over S, because we had to make the whole system a type 1 system, because when we closed the inner loop we got 1 over S squared plus K here. And so part B says, using DC from part A, what class of disturbances can you reject with 0 steady state error? Okay? So what we need to do is, remember when we're doing disturbances, we assume that R equals 0, and we twist the entire system. So what you do is you put the disturbance W here, okay? And then what comes out of W? 1 over S squared plus K. And then you're going to get Y here, and then Y is going to come down here. And then because R is 0, and remember, you got to put a plus minus. I'm just going to draw it just so you see. So you get this Y comes down here, negative, and then this comes in here, R plus. But this is 0 now, so that's eventually going to go away. And then the output is going to be E, which hits DC, K2 over S, and then that comes back in here, plus, plus. Now, because this is plus plus, and when you're doing the feedback rule, you want plus minus, really this minus is going to come, this is going to go away, so that's just going to go away. This minus is going to turn into a -1 block, but -1 can get multiplied by this, and then that negative can get distributed up here, and so what we can do is we can just get rid of this whole block and change this to a minus sign. And then our control block diagram basically is exactly how it was before, where this is G and this is H. Now you could, the idea is what kind of disturbances can we reject? Can we just reject impulses, constant disturbances, ramp inputs, what can we reject? We already know that if R is a step, we have 0 steady state error. We know that because it's a type 1 system. If R is a ramp, we are going to have constant steady state error. And if R is a parabola, our ESS is going to go to infinity. Okay? So the question is if W is a step, what happens to our system, right? That's what we want to know. Okay? So if we take a look at this, right, the easiest thing, at least for me to do when I do these types of systems, is close the block, okay? So I'm going to assume that's G and that's H, and I'm going to say my closed loop system is is G over 1 plus GH, and so I get 1 over S squared plus, that's terrible, 1 over S squared plus K over 1 plus G, which is, so I'm going to get K2 over S, S squared plus K. So the K2 over S is the H part, and then the 1 over S squared is the G part. I multiply the top and bottom, and this is where things get kind of weird. The denominator here and here are actually different, and so in order to get rid of the improper fraction, I actually have to multiply by S squared plus K, okay? And so what's going to end up happening is my closed loop transfer function is actually going to be S in the numerator, and in the denominator, I'm going to get, let's see, S cubed, ooh, I get a third order system, plus KS plus K2. When I was doing this with students, I would ask them if that's right. They're not here, so I guess I'm going to check myself. So let's, you're going to get an S cubed here, a KS here, and then that cancels with that, so you get K2, okay? So there's no type system here, So now we can do final value theorem. So if W is a step, W equals step, right? The final value is going to be what? Well, in order to get the final value for a step, you plug in S equals 0, and you're going to get that the final value is indeed 0. Because if you plug in 0, you get 0 in the numerator, you're going to get 0 over K2, which is this 0. So that means, I'm not really, when you're doing disturbances, you're not really looking for steady state error. What you want to know is if the system comes back to 0. Do you reject the input? And so what I really want to know is what's the final value, or what, yeah, I mean, you want to know error. You want to know, what do you want to know? It's not necessarily error. How do they do it in the book? They say reject the disturbance. I'm going to say the final value, right? Yeah. They want I want to know what X steady state, or in this case Y steady state is. I forget what the book says. This is what I want. I want the Y steady state to be 0, and in this case it is. Okay. Another way you can look at it is you can see that G closed loop is Y over W, right? That is S over S cubed plus KS plus K2, right? If W is a step, right, W is going to be 1 over S. Well, if you factor that in, Y is going to be 1 over S cubed plus KS plus K2, right? Now this, if you inverse Laplace this is going to be 3 stable poles, right? So you're going to get, AE to the negative S1t, BE to the, if you inverse Laplace, B to the negative S2t, CE to the negative S3t, and all of these are going to go to 0 as t goes to infinity. So you're going to reject that disturbance, okay? So then the question is what happens if W is a ramp? Okay, well, so now things are different, right? So now if you, I need my phone to take a picture of this. Whoop, wrong thing. Let's see, Rocketbook, let's see, beacons. Board notes. For those of you that don't know, by the way, these are beacons by Rocketbook. I think they're like 25 bucks. They're amazing. You just stick them on the board. They use space age Velcro, and you can just upload your notes to Google Drive, which is what I'm doing now. And if you pay tuition for my class, you would get these notes. But if you're not, then you can just watch them on YouTube. Okay? So we already know that if W is a step, Y steady state is 0. Okay? So now what happens if W is, I'm going to get rid of this, get rid of this, get rid of this, get rid of this. Actually, I'm just going to get rid of that. Okay? So what happens if W is a ramp? So if it's a ramp, it's 1 over S squared. Okay? So then Y is going to be 1 over S cubed plus KS plus K, and I think one of these is K2. And so now if you do partial fractions, you're going to get A over S, B over S cubed plus KS plus K2, and if you inverse Laplace, you're going to get A plus BE to the negative plus 1t, CE to the negative S2t, plus DE to the negative S3t. Where did B, C, and D come from? They're just random coefficients. Why? This is going to have 3 poles, and I'm assuming that you're intelligent and you pick K and K2 to make the system stable. You make all 3 poles in the left half plane somewhere, and no matter what, as long as they're in the left half plane, all of these are going to go to 0. This, on the other hand, is not. It means that the steady state value of Y is A. So if W is a ramp, you're going to have constant steady state error. Okay? So this is interesting, right? Like if you go back to what our system is and how we're rejecting our controller, if we if we design the controller to be like this, we're going to have 0 steady state error to a step, and we're going to be able to reject step disturbances to the system. And it also means that if we hit it with a ramp, we're going to have constant steady state error if we hit it with a ramp, and we're going to be able to at least have constant steady state error to a ramp this way. If you wanted to completely reject a ramp input, you would have to have a type 2 system, and you'd have to increase and put 2 integrators in the system. Okay, hopefully that helps and you understand this problem now. This video is getting kind of long, so I'm going to go ahead and stop here. If you have any questions, post them in the comments.